We now try out a slightly different kind of sampling, which we hope will ameliorate some of the problems that we have encountered with flat top sampling. Now, this is a nomenclature that is, I think, unique to me, but I like to call this faithful top sampling. Let me demonstrate with a figure. Let x t be as usual something of that shape. So, this is x t. Now, we want to have a sample train that consists of non-ideal pulses, that is to say rectangular pulses, but these pulses will be exactly equal to the values of x t at the points where they occur. Let me show what that means. That was one pulse. Second pulse, and so on. Essentially, it is like this. This I will call x t of t. X t of t equals x of t when mod t minus n t s is less than t and it equals 0 when mod t minus n t s is greater than equal to t. Fine. So, this is the definition of the faithful top sampled sequence, the sample train, faithful top sampled train. The rectangular sampling technique that we discussed before was called flat top sampling, and there it was flat at the tops of the samples of the sample pulses. Now, it follows the contours of the signal. This might seem like a very minor difference, but it turns out that it makes a considerable impact on the spectrum of the sampled signal. Now, the first question we have to ask ourselves is, how do we construct this faithful top sampled signal? Now, for the rectangle sampled case, for the flat top sampled case, what we did was we constructed the ideal impulse train first, x s of t, and then convolved it with a rectangular pulse. Since it was a non-causal rectangular pulse, each impulse was replaced by a rectangular pulse of width 2t, and therefore, it was flat at the tops. This is what we did. Now, we have to have something that is slightly different. What we do is we take a rectangular pulse train. The basic rectangular pulse, as we know, is R t of t, which is equal to 1 if mod t is less than t and equal to 0 if mod t is greater than equal to t. This is the rectangular pulse. Now, we want to have a train of such pulses. That is to say, we will construct a function which is summation over all n r t of t minus n t s. This we shall call, say, P t. We shall call this P t. It is a rectangular pulse train. Finally, we can show that the faithful top sampled sequence, sample train x t of t is given by x of t multiplied by p of t. This is the way we can mathematically express the form of x t of t. But then how do we go about generating this? थोड़ा भूल गया. So, the first step is to get P t. Which is a periodic repetition of the fundamental rectangular pulse r t of t. Now, how is that achieved? Well, we take the original impulse train, which is d t, and simply convolve it with r t of t. So, P t equals r t of t convolved with d t, which means of course that p omega will be equal to r t of omega multiplied by d of omega. Now, let us go back and recall for the nth time what is d of omega. D omega was 2 pi by T s summation over k delta omega minus k 2 pi by T s. This was d of omega. R t of omega was given by 2 times sin omega t by omega, right. So, we now have both of these and we have to multiply them. So, let us sketch each of these functions and see what their product begins to look like. First of all, d omega. Now, the impulses that are components of d omega are placed 1 by T s or rather 2 pi by T s apart from each other. Since T s is believed to be considerably larger than T, which is the width of the modulating pulse, the rectangular pulse, it follows that 1 by T s will be much smaller, and hence we expect 2 pi by T s spaced pulses to be much closer to each other than 2 pi by T. So, let us first make, this is the omega axis, this is all the frequency domain in which things are happening. Let us first make a plot of these functions. So, if this is omega equal to 0, this is at 2 pi by Ts, 4 pi by Ts, minus 2 pi by Ts, and so on. It is at these frequencies that these frequency domain impulses related to d omega of t or d of omega are present. Now, let us say that capital T, which is the width of the rectangular pulse, is 1/4 of capital Ts. So, let Ts be equal to say 4T. That is just a matter of convenience, it often could be even higher. Now, if Ts is 4T, now let us go back to the equation for RT of omega. Now, RT of omega is equal to 2 sin omega t by omega. Where are the minima? Where are the not the minima, but the zero crossings of this function? The first zero cross, there is no zero crossing at omega t equal to 0. The first zero crossing is observed at omega t equal to pi and minus pi on the left and right respectively, right and left respectively. So, when omega t equals pi, you find that omega must be equal to pi by t, right. Next, when omega t equals 2 pi, you again get a zero crossing. So, omega then omega equals 2 times pi by t, and so on. Essentially then the minima, the zero crossing, sorry, of RT of omega are at plus or minus k pi by t, plus or minus k pi by t. We can just say k pi by t. Are at k pi by t, all right. So, now since Ts is 4 times t, we find that the first place, the first zero crossing on the same coordinate frame will be found at the place where you can find pi by t. So, the first this is a sinc function which will have zero crossings, and the first zero crossings of RT of omega will lie at omega equals plus or minus pi by t, which is equal to since t is equal to Ts by 4, you get 4 pi by Ts. So, let us see where is 4 pi by Ts. This is the place. And let us now use a different color, say this. So, this is the first zero crossing of pi by t, and similarly on this side, this is the first zero crossing of pi by t, this place. Okay. So, now between these two places you have the curve of RT of omega, which is a sinc function. So, it will be a function that goes like this. and then the next 0 crossings will be at 8 pi by Ts, that will be here and here. Let me put one more. So this is the next place where you will find the 0 crossing of this function. So you will get something like that goes like this, and here too you will get something that goes like this, and then goes on like this, goes on like this. So that's the layout of this new function, which is RT of omega. This is RT of omega. Now remember that we don't convolve these two functions, we multiply them, and when you multiply them, all that happens is that the impulses in d omega get appropriately modified in amplitude by the amount of the value of RT of omega at that respective place. So you get new vectors. We will just draw them over here in, say, blue. You have this, and then you have zero at this place and at this place, then you have and so on. So the blue function is actually RT of omega multiplied with d of omega. This is what we have just drawn. As also this, for example, and all the other impulses of various heights in the train. So this is d omega times RT of omega. Now what do we finally do with this? Let us get back to the original equation. We had, for faithful top sampling, a multiplication of xt, that is x t of t, the faithful top sample train, was equal to xt multiplied by d of t convolved with RT of t. So now that we have evaluated the transform of this, we just have to see what to do about the multiplication. Well, using the modulation property, it is pretty straightforward. We find that x t of omega equals 1 by 2 pi x omega convolved with this function d omega multiplied by RT of omega. D omega multiplied by RT of omega is already here in terms of in the form of these blue impulses. This has to be convolved with x omega. That means, at each place where you have an impulse of d omega multiplied by RT omega, you create a copy of x omega, a shifted copy of x omega, which is also scaled by the appropriate value of the height of the pulse d omega RT omega. Thus, for example, if let us say we plot x omega over here against omega, and we get a function that looks like this. Let us say x omega was like this. So, this is minus b and this is b. Suppose this is what we had. Then you will find over here a tall alias let me just change the color. I think it does not look appropriate, it is confusing us with something else. Let me choose different color for this. Let me do it out of yellow or cyan. Okay. I hope everybody can see this yellow color, but it is there. There is an yellow pulse over there. Now, we want to make yellow triangular pulses at each place, but the height of the pulses will be different depending upon the height of the local impulse of d omega times RT omega. Since each of these is of different height, we will get one impulse like this, one pulse, one copy like this, another slightly shorter over here, then there is 0 over these two places, then there is a negative pulse like this over here and here, and then again a 0 over here and over here. So, this is what we are getting. We observe the following. Well, what we have just plotted in yellow is x t of omega. X t of omega is the final spectrum of the faithful top sample train. That is the spectrum of that. Now, what can we say about x t of omega? X t of omega consists of aliases of different amplitudes. With the central alias being the strongest. With the central alias being the strongest. A more important observation than this is the following. Each alias apart from the modification in amplitude is a faithful replica of x omega. There is no distortion. We should put this in capital letters. There is no distortion. If I may say more pointedly, there is no distortion, unlike in the flat top sampling case. There is no distortion in the faithful top sampling case. So, faithful top sampling has solved the problem of distortion. If we can have an ideal low pass filter to retrieve only the central alias and reject the others, then we have, assuming of course that we have followed the sampling theorem, we have exactly what we want. We have the central alias taken out. So, you get a copy of the original function. Fine. So, let us write out the expression for x t of omega. X t of omega equals 1 by 2 pi times the convolution of x omega with the impulse train, that was the modified impulse train r t omega times d omega. Now, r t omega times d omega will essentially be equal to, first of all let us write that expression, r t omega times d omega is equal to summation overall k 2 sin omega t by omega multiplied by delta omega minus 2 pi k by T s. This is r t omega by d omega times d omega. This is an impulse train of varying heights, and this is now convolved with x omega to get x t omega. So, x t omega is 1 by have we missed something over here? I think we have. This is actually 2 pi by T s. D omega also has a multiplying factor of 2 pi by T s outside. So, you have this as r t omega times d omega, and now we have over here x t of omega given by 1 by 2 pi convolved with this. That means, at every pulse over here, at every impulse over here, we replace x of omega minus 2 pi k by T s. So, you get this times 2 pi by T s summation overall k of 2 sin omega t by omega times x of omega minus 2 pi k by T s. This is the expression where of course 2 pi may be cancelled, so that we finally get x t of omega equals 1 by T s summation overall k 2 sin omega t by omega multiplied by x omega 2 pi k by T s, omega minus 2 pi k by T s. Now, this gives all the aliases of x t omega, but we in the process of reconstruction or retrieval will get rid of all except the central alias. So, we will apply the following: by low pass filtering, with L omega given by L omega equal to T s for mod omega less than b equal to 0 for mod omega greater than equal to b, what do we get? We get x t omega multiplied by L omega, and when you do the multiplication, you find that every alias other than the central alias is out of the picture. So, you simply get now with T s cancelling the T s in the denominator in x t of omega, you just get x let us see, sin omega t by omega evaluated at omega equal to 0 will give you 1. So, you have 2 x omega. That is it. You have practically got what we wanted, except for the scale factor of 2, which can always be adjusted. So, faithful top sampling is capable of undistorted retrieval. Faithful top sampling followed by ideal low pass filtering will yield an undistorted output. Equal to 2 x omega.